Here's a problem from homework that nobody asked about in class, and it's got a couple of really important things we need to discuss. So I want to go over it. It's number 24 from section 3.2. So problem 24. The reason I want to look at this one is it's an easy one to do enough by hand. You don't need anything. I do have the graph over here just so we can look at it. But the other reason is it gets into the bounded regions, which is important for us for the extreme value theorem. That I've got two mins, you can see just by looking at it, two mins here, and a relative max, not an absolute max. This is just a relative max. These two mins here are absolute minimums, and they're the exact same value. But it's going to be important for us to establish the fact that we have more than just relative mins and maxes because of the fact that this is a closed interval. So we have to look at both intervals. So the first thing you would do is find the domain to look to make sure there's nothing left out. We look for critical numbers, so we don't have to exclude any values. Well, it's a polynomial function. There's nothing we're going to leave out. So we have that taken care of. Next thing we do is we just find our derivative. So f prime of x is 4x cubed minus 16x. Okay. Now, in order to find critical numbers, you either find the derivative equal to 0 or make sure it's undefined. Well, in this case, again, polynomial won't be undefined ever. So we can just set it equal to 0, and then to solve, take out 4x. That gives us x squared minus 4, which when we factor that gives us x plus 2, x minus 2. So our three critical numbers are 0, negative 2, and positive 2. So critical numbers, x equals 0, negative 2, positive 2. Now, when we look at part A of this, it says to use the interval negative 3 to 1. So that's only going to encompass two of our critical numbers because 2 is not in that interval. So for part A, what I'll actually have to look at on my sign chart is negative 2, 0, and then I'll have to include 1 and negative 3, but only because those are the boundaries. I'm not actually going to do left or right of those numbers for the signs of the derivative. I'm just going to check around there and kind of think about that as an endpoint. So I know I have 0 slopes for both of those. Okay. Between negative 3 and negative 2, I could choose a number like, say, negative 2.5 and plug it into the derivative, which actually, I'm sorry, is plug it into this function right here, the derivative, and evaluate it and see what kind of value I get. Actually, the easiest thing to do is really to think about it in terms of this guy, because whenever you plug in, say, like negative 2.5, this will be negative. This will be negative as well. This will be negative. All three of those values will be negative. So it'll be negative times negative times negative. I don't know the exact value. I don't even care. I just know that it's going to be negative times a negative, which means a negative value. So the slope here is negative, which you can see on the graph right here. Between negative 3 and negative 2, it's got a negative slope. Then I do the same thing between negative 2 and 0. So say something like, I don't know, negative 1. Okay, now when I do that, this will be a negative. This will be positive because it'll be negative 1 plus positive 2, and then negative again. So it'll be negative times negative, which gives us positive slopes, which again you can see here. Okay, it's positive slopes. And between 0 and 1, I can pick a number like x equals 1/2, positive, positive, negative. That gives me then negative values here, which again you can see in the graph. Okay, so again, if we didn't have the graph, which on your tests and quizzes at times we won't be given a graph, you'll have to do this on your own. That's a way we can do it without just plugging the numbers in, just to save yourself a little bit of energy and time. So I know this is going to be a relative min. This will be a max. But what I don't know is if these are absolute or not yet, because I haven't evaluated at these 2 points, nor have I evaluated at the end points. So I have to do all three. I have to do f of negative 3, sorry, all 4. F of negative 2, f of 0, and f of 1. I have to find all 4 values because I've just found the critical numbers. I haven't found the actual max or mins. So f of negative 3, just to save us some time because it's video. Again, the trick is do it quicker. Plug in the function into y1, x to the 4th minus 8x squared. Dang it. X to the 4th push over minus 8x squared. Scroll over plus 2. And now y1 of negative 3 is 11. Second entry pulls that back up. That's why this is nice. y1 of negative 2 is negative 14. You don't need to do it for 0, but might as well, because it just makes it easy to do then. But 0 should give you 2 back because everything's going to cancel off except for the 2 left over hanging out over here. And then f of 1 will be 1 minus 8 plus 2. So 1 minus 8 is negative 7 plus 2 is negative 5. But just to make sure that Mr. Moyer can do his arithmetic, negative 5. So in our graph, this is our absolute minimum. This is actually our absolute maximum. Okay, and that was one of the parts of the extreme value theorem, is that if you have bounded regions, you're guaranteed to have a maximum and a minimum. Now in this case, our absolute min was the absolute min of the graph, right here at negative 2, but the maximum, which should have been a local max at 0, is no longer the max. It's actually just it's just a local max, I guess technically when we get into it. This would be a local max, or relative max, and this would be relative min. Okay. But we were guaranteed an absolute max and absolute min. Then for part B, we do the same thing. But now when we do our sign chart for part B, because we are between negative 1 and 3, we'll exclude negative 2. So go through, do the whole thing again. Make your sign chart. Negative 1's the lower bound, 3's the upper bound, 0 and 2 are the other values to check. Again, 0 for that and that. And just through doing the problem, you'll get that this has a positive slope, negative slope, positive slope. So again, checking our bounds and doing f of negative 1, f of 0, f of 2, f of 3 to check and see if it's max or min. So that's something to be aware of. Don't forget to check if it's bounded or not, because if it's bounded like this region is for A and B for this problem, you're going to have a guaranteed max and a min, not just a local one.